Okay, I want to just take a couple minutes here for those of you that are interested to show you how um, our definition of gravitational potential energy lets us, or the equation that we have lets us deal with an extended object as just a point mass located at the center of mass. So when we use this equation, gravitational energy is equal to mgh, where h is just some height above an arbitrary zero. Even if we have an extended object like this, like a vertical bar, for example, we can just pretend like this is a point mass, as long as we think of that point mass as the center of mass of this object. So let's start with a simple case here. Take a vertical bar like this. Let's say this location here is what we call H, and we'll say that that's where the center of mass of this bar is located. So it's right in the middle. This is a uniform bar. It's exactly the same along every piece of its length. And let's say that it is length L. This height here would be h minus half the length of the bar, and then this here would be h plus half the length of the bar. And then down here we would have the ground, and this is what we would be calling height 0. So what I want you to do is to think about the total gravitational energy of this thing as just the sum of a bunch of little chunks of mass delta m. All right, and if we think about this bottom chunk here, delta m, the gravitational energy, UG, would just be equal to mgh. So in this case, this little mass delta m, uniform gravitational field g, and the height would be h minus L over 2. Right, for the top chunk, same thing. It would be delta m g times h plus L over 2. Okay, and then if we're thinking about the whole bar, we're just going to make a whole series of these little chunks and add them all up. And the sum of all the delta m's will give us the mass of the whole bar. And what I want you guys to see is just if we think about these two, if I add these terms together, this one and this one, what I'm going to get from just these two chunks is this sum, delta mgl plus delta mg, oops, sorry. I'm sorry, that's not what I'm going to get. I'm going to get this, delta mgh plus delta mg L over 2. That's from the top chunk, just multiplying out across those parentheses. And I'm going to add to that the bottom chunk, delta mgh minus delta mg L over 2. And so this cancels this, and all we have is delta mgh times 2, because we've got two of those little chunks. So what you can think of is this thing is symmetric. For every chunk on the bottom, you're going to have an equivalent chunk up on the top, and the kind of loss in height of this one will be canceled by the gain in height of that one. And so we can infer that if you add up all these chunks, you're just going to get mgh as the gravitational energy of this whole thing, where m is the mass of the whole bar, and h is the location of the center of mass. Okay, so that's kind of a little hand-wavy argument. You can see how it works out. But if we want to be correct, we should actually add up. I mean, if we want to be technically correct, if we want to prove this thing, we should add up an infinite number of chunks of infinitesimally small mass. And that means that what we should really be doing here, we're really doing a sum of infinite parts here. We should be doing an integral. So let's look at this from an integration perspective here, and that's as far as we'll go. So now let's do some calculus. Okay, so we're going to take the same setup. Think about a uniform bar. We'll define the center of mass right at the center. We'll say it's length L. We'll call this height h, and again, this will be the extent of the bar. Will go down from h to h minus half the length, and the top of it will be h plus L over 2. And what I want to do is take this sum that we had thought about in the last one, delta mg times h, where h is the location of each chunk of mass delta m, and turn this thing into an integral. We're integrating infinitesimally small chunks of mass dm. We're going to integrate over the extent of the bar, and then each one of these gets multiplied by g and h, where again h is the location of this chunk of mass dm. This is very similar to what we were talking about when we looked at integration for moments of inertia. You don't integrate over masses, you integrate over coordinates. So our job is to write the mass of this rod as a function of its location and extent in space, and so we're going to define this linear mass density, which is just equal to the mass of the bar divided by its length, because this is a constant, and this is only true for something that's a uniform bar like this, a one-dimensional object. Right? So this is the linear mass density, and it would tell us something like how many kilograms the bar is per meter of bar that we have. All right, so we can rearrange this thing. Lambda L is equal to m. Lambda is a constant. We're going to take the derivative of both sides of this thing. So we get lambda dl is equal to dm. The linear mass density times a tiny little chunk, an infinitesimally small chunk of this thing, will give us the mass of a tiny chunk of this bar. Okay, and now we do the integral. So that's going to look like this. We're integrating h minus L over 2 to h plus L over 2 of dm g h. That's our gravitational energy. We're going to substitute now over the same limits. dm, we're going to substitute lambda dl times g times h. Or we can think of this h really as the coordinate that we're going to integrate over. So I'm going to substitute that with an L here, because these two are the variables that are changing as we think about kind of adding those things up across the length of this bar. Okay, so now we integrate. Lambda and g are constants, so we can pull those out to the front. And so we're really just integrating L dl. Right? So I want to think of, what thing's derivative is equal to x, or in this case, what thing's derivative is equal to L. So I raise the power up by 1, and then I got to bring that half down in the front, so that when I take the derivative of this, bring down the power, this goes away, and this becomes L, which is exactly what I want. So I have lambda g times 1/2 L squared, and I'm going to evaluate that function from h minus L over 2 to h plus L over 2. So that's going to look like this. Again, lambda g is just a constant, so I can drag that out in the front. The half is a constant, I can put that out here. And then I have this final minus initial, so h plus L over 2 quantity squared minus h minus L over 2 quantity squared. Now I gotta do all this algebra. So h squared outside inside plus h times L plus L squared over 4 minus h squared outside inside minus 2hl plus L squared over 4. Clean this up on the inside, h squared minus h squared. Oh, I'm sorry, this shouldn't be 2. This is h times L over 2 plus h times L over 2, so that's just h times L. This is plus, and then this is going to be plus, because it's minus. Distribute that, so we're going to have 2HL. And then the last one here, we've got plus. Distribute the minus sign, it's going to be minus, so that goes away too. So what we have is 1/2 lambda g times 2HL. This goes away. This. So our final UG is expressed like this, lambda g h L, which almost looks like what we want. We want to show that this is really just mgh, where h is the location of the center of mass and m is the mass of the whole thing. But remember, when we defined lambda as the mass of the rod over L. We can substitute that, or where L is the length of the rod, substitute this back in, m over L times g h times L. Cancel, cancel, so we get, great, mgh is the gravitational energy of this rod. Now kind of formally defined, we've thought of all of the chunks of mass. We haven't made any hand-waving arguments or doing calculus to show this. So at the end of the day, what's important is that if you know where the location of the center of mass is of an extended object, no matter what that object looks like, if the center of mass is like this, you can talk about the gravitational energy of this entire thing by treating this thing as a point mass located at the object's center of mass, and then the full gravitational energy of this thing would be equal to just mgh. That's the total mass, and this is the height of the center of mass. If you go back in your book, you'll see that the center of mass is formally defined as an integral as well. And so if you are locating that center of mass, you're doing this integration whether you know it or not. But again, the more important thing is that you know how to use the result of that, not necessarily that you know how to do the calculus that gets there. It's satisfying if you do it, if you enjoy that stuff. If not, you can still do a whole lot of physics with the final result. Okay, that's it. Thanks for watching.